Okay, so we're going to talk about the squeeze theorem. And so we have this picture, and we're going to picture that this is our unit circle. And then we have a little coordinate plane. So when we're talking unit circle, this point right here is going to be 1, 0, which is going to make this 1. And then when we're talking unit circle, any point on the unit circle is going to be cosine sine. So instead of x, let's use theta here because we have theta in our problem. All right, so a couple things that we want to go through here first. So we're going to look at kind of sections of this graph, and the first section that we're going to look at is this full triangle right here. Okay, so when we look at this full triangle, we know that if I'm looking at theta, for triangles, tangent is going to be opposite over adjacent. So in this particular case, my opposite side of theta is this one. My adjacent side is this one. So it's going to be opposite, which we don't know what that is right now, over adjacent, which is 1. Okay, and so if I want to figure out what that opposite side is, opposite divided by 1 is just going to be opposite. So this tells me that tangent is actually going to be that opposite side. So this point here is going to be 1 tangent theta. Okay, and so that's going to help us when we come over here to this red triangle. And we're going to find the area of that triangle. Area is 1/2 base times height. So we're going to have 1/2. Our base is going to be 1, and our height is tangent. So we're going to have 1/2 tangent theta, which we could write as just tangent theta over 2. Okay, so the next section that we want to look at is we're going to find the area of this sector, this curved sector here. And so to figure that out, what we can look at is the fact that this is kind of like a piece of a pizza, right? Or like a piece of a pie. And so this entire circle is 2 pi. Okay, and so this is going to be theta over 2 pi of, that's going to be the fraction that we're looking at, this highlighted area. Okay, so that's the fraction of the whole circle. Okay, and then what we're going to do is we're going to multiply by the area of the circle. So we just want this one fractional piece. We want the area of that fractional piece. So if we can take whatever fraction that is of the circle and multiply it by the total area, then we can get what the area of that fraction is. So the area of the circle is going to be pi r squared. So pi times 1 squared, that's the area of the circle. And so when we multiply those, we're going to get theta pi over 2 pi, which is just going to be theta over 2. Okay, then the last section that we want to get an area of is going to be, let's draw a line here, okay? And we're going to get the area of this inside triangle right here. And so what we're doing here is we're going to get the area of the big triangle. We have the area of the sector and then the area of that small triangle, and that sector is sandwiched between, so it's in between the other two areas. And so this is going to help us figure out the area here. And so when we're looking at this triangle, if we draw a line straight down here, we know that that point is cosine theta sine theta. So the height here is going to be sine theta. The base is still 1. So 1/2 base times height. So we're going to get sine theta over 2. And we'll draw some inequalities here, right? So we have this big triangle. So the big red triangle is bigger than that middle sector, which is bigger than the smaller triangle. Okay, and we're just going to do a little bit of manipulating. So we're going to multiply by 2 over sine theta. Okay, so when we do that, okay, so we know that tangent is sine over cosine. So we have some 2's that are going to cancel. So we're left with 1 over sine theta times sine theta over cosine theta. So these sines are actually going to cancel. And we're going to be left with 1 over cosine theta. 2's will cancel here, and we have theta over sine theta. And then all of this is going to cancel to 1. Okay, so we have this little thing where we know that cosine theta, so if we plug numbers in, okay, when we take the cosine of theta, it's going to equal the cosine of negative theta. Also, the sine of theta over theta is going to equal the sine of negative theta over negative theta. Okay, so this inequality is valid for all non-zero theta in the open interval negative pi over 2 to pi over 2. Okay, so essentially in this interval, negative numbers are not going to mess up these results. Okay. Okay, so we have this 1 over cosine theta greater than or equal to theta over sine theta greater than or equal to 1. So then if we decide to take the reciprocal, okay, so take the reciprocal, that's going to give us cosine theta. We need to flip our signs when we take the reciprocal. Then we'll have sine theta over theta, and then we'll still have 1. Okay, then if we decide to take the limit as theta approaches 0, Okay, and if we think about the limit, okay, so if I plug 0 in for cosine theta, I'm going to get 1, okay? So this limit, as theta approaches 0, of cosine theta is going to be 1. The limit as theta approaches 0 of 1 is 1. And so what happens here is I have this scenario where I know that I have an area bigger and I have an area smaller, okay? And so my area here, this area is sandwiched between these other areas. And if those areas are both 1, and we know it must be between that, then it has to also be 1. They must all equal each other. And this is the premise of the sandwich theorem. So I have these graphs that I'm sandwiching together, and because I know the limit of one of them and the limit of the other one, and I know that the other one is sandwiched between them, then I have proven that that third one must also equal those other two outsides. And so what we've also proven is we've proven this rule that we've been using, where we know that the limit as theta approaches 0 of sine theta over theta is 1.